All right, so I'll pass out the notes, but before I pass it out, I want you to have a conversation with your group mates about what you see here. F of X is a chocolate chip cookie. G of X is ice cream. F of G of X, G of F of X. Turn to your group mates. Say good afternoon and talk to me about what I'm going for here. Marcus, let go.
This is where we had
I remember doing this in
Irish? I thought it was British. Is it Irish people or British people that have T in the end?
Yes.
It's British people.
Okay, thank you.
It's typically an English thing,
Okay.
but it's interesting when you talk about the United Kingdom.
I forgot about that.
Yes.
It's confusing. There's like
It is
England
very
and then there's
confusing.
United Kingdom and then there's like.
Yeah, it's just the same as Canada's kingdom sometimes, so we get it. Alright, so did everybody get it? Alright, conversations about f of x, g of x, f of g of x, and g of f of x. What say you? We did. You definitely did this in Algebra 2. Keep going. Keep going. Talk to me. Come on. No pencil should be going. Your pencil's down. Your eyes are up here. You're engaged. You're ready to learn calculus. We're playing a game today, so come on. We're going to have some fun. Talk to me.
About the
Yeah. If this is f of x and this is g of x, how is this f of g of x? And how is this g of f of x?
G of X is like sandwich, and the ice cream is sandwich, and G of X is sandwich.
Okay, so this g of x is our ice cream, and that ice cream is sandwiched in between, Caitlin says, sandwiched in between those chocolate chip cookies. So it's embedded. It's a part of it. So when I go to take a bite, I get cookie and ice cream all in one. Not cookie, and then I take a bite of ice cream. One is embedded inside the other. Talk to you about g of f of x. The cookie's embedded in the ice cream. So we're going to talk today about composite functions, and I love this picture because this ice cream is my outside, or my parent, and this cookie is my inside. For my f of g of x, the cookie is my outside, and the ice cream is embedded inside. Make sense? All right. So if you look at today's notes, we'll go ahead and work through these together. We'll close this out because that was so fun, looking at those pictures. And we'll go ahead and we'll say that we can take the derivative of a composite function. So we're going to learn something today called the chain rule. And the chain rule is going to be like a chain where it keeps on going and going and going. Some people prefer to describe it as an onion that has all kinds of layers in between. If you're a Shrek fan, what does he like instead? Oh, come on, any Shrek fans? He says ogres are like onions, and Donkey doesn't like it. So what does he say? They're like what? Seriously? No Shrek fans? When he says parfait, everybody like parfait. Are you with me there? Yeah. So when we're talking about a composite function, that's a function that's formed when one function is substituted into another function. So when you were in Algebra 2, you learned this notation, f of g of x, and then here, of course, we have g of f of x. And what that means is that whatever x value has to go into g, and then whatever that output is what then goes into x. So when we have that f of g of x, I can't figure out what f is until I figure out what g is. The output of g becomes the input to f. So let's go ahead and make sure we understand that the output of g of x becomes the input of f of x. So a little algebra 2 review. Here we have two functions. My first function is f of x is equal to 3x plus 2. And my second function is the opposite of x squared plus 3 is g of x. So when I'm talking about f of g of x, when we teach this in algebra 2, we go ahead and we start with f of, and then we switch color pens, g of x, and we make sure that they understand that this 3 and then this input is going to be g of x is that input, the opposite of x squared plus 3. So seeing it with the different colors tends to help, friends. Now in your baskets you should have at least a red, a blue, and a green of the colored pencils and some highlighters. So I am obviously a firm believer in colors. I think colors help significantly. So what I would like you to do is, if you find this helpful, go ahead and delineate between your two functions. Because once I see that, then I know that it's the opposite of 3x squared plus 9 plus 2, and I get the opposite of 3x squared plus 11. Once I embed that function into each other. Now the cool thing is, if I had a value for x, then whether I plug it into g and then x or f of g of x, it would be the same. Let's test it out. Let's go ahead and suppose that x has a value of, let's keep it simple, and say x has a value of 1. If I do the opposite of 1 squared, that's negative 1, plus 3 is 2. When I put 2 into my f function, 3 times 2, 6 plus 2 is 8. So when I do it the long way, I get 8. Now we'll go ahead and try this. Stick 1 into x squared. 1 squared is 1. Times negative 3 is negative 3. Negative 3 plus 11 is, phew, that means we did it right. So when we're talking about embedding a function, we want to make sure that we can figure that out. And I'll show you that math over here. If I said that g of 1 is equal to the opposite of 1 squared plus 3, which is equal to 2. And then I understand that f of 2 is going to be 3 times 2 plus 2, and that's where I got that 8. This output becomes this input, and this is my overall input. And I can test that here by saying negative 3 times 1 squared plus 11. Sure enough, I get the same value, which means I did my algebra correctly. Not a worries. Not a worry. We are masters of algebra. That's why we are sitting in calculus. So we're not worried about that. Note the notation. I'm not a fan of that notation. I find I mess it up, and I will always rewrite it, f of g of x, just to keep track of what it is I'm plugging into where. How am I doing? Okay? All right. So go ahead, you do g of f of x. Talk to your group mates, agree on it, and test it to make sure you got it right. Go. All right, so here it is, color-coded. if my G function is my purple function, and if you watched me write this, you can see I left this blank, finished writing my function, and then came back to write it in. Now when it's time to solve, I want the opposite of 3x plus 2 times 3x plus 2 plus 3. Hey, this is binomial multiplication that I need to FOIL. You're like, what? That's a lot of work. You got it. So my first term's 9x squared. My outside and inside terms are the same. 6x, when I add them together, I have 12 x's. And then my last terms is 4 plus 3. This negative outside is just waiting to say, nuh-uh, that's negative 9x squared minus 12x minus 4 plus 3, because he gets distributed across the entire function. So now when I summarize, I've got the opposite of 9x squared minus 12x. These two constants can be combined to minus 1. Again, if I wanted to test putting a function in, I could pick a test point like x is equal to 1. And I would have to first put it into f of x. So f of 1 becomes 3 times 1 plus 2. F of 1 is 3 plus 2, or 5. Which means my g function becomes g of 5. Which means I want the opposite of 5 squared plus 3. So 5 squared is negative 25. Negative 25 plus positive 3 is negative 22. Did anybody put 1 in here? Do I end up with negative 22? It's like the moment of truth. So that's negative 9 minus 12 minus 1, definitely negative 22. So I do this, what's in orange, as a test to see if I did it right. All right, some more practice for you. Use this table below to find the following function compositions. Here is my input. So those x values have an input of 1, 2, 3, and 4. And what I have is a lot of different ways of writing this. So I want you to think about that ice cream and chocolate chip cookie example. 3 goes into T, and that output goes into S. 3 goes into S, and then that output goes into T. 4 goes into S, that output goes into T. 1 goes into T, that output goes into S. With your groups, go ahead, tackle this on your mark, set, go. All right, so check it out. With each of these values, you start on the inside. This is the inside, so 3 goes into T. So my input of 3 on my T function gives me an output of 2. That means that that output is the input of S. So S of 2, 2 going into S, gives me 8 as an output. Your function notation is super important because it helps you keep track of what inputs and outputs you're dealing with. Sound okay? Now, again, this type of notation, this here and this here, I sometimes struggle with. So I go back to how I know it's to be read. And to me, when I read it that way, it makes perfect sense when I say S of T of 1. I'm going to take the time to rewrite this as this because this means plug 1 into T and take that result and then plug it into S. Same thing here. This is T of S of 3. I'm going to take 3 and put it into S and then take that output and put it into T. Now, when I put 3 into S, the output happens to be 3. So don't let those 3's confuse you. How we doing? Everybody good with this Algebra 2 review? We love Algebra 2. Turn to your group mates and come up with one word to describe your Algebra 2 year. Your mark is set, go. All right, come back. Remember when you thought Algebra 2 was hard?
No.
All right. So here's the deal. We're going to learn something called the chain rule. And the chain rule allows you to take the derivative of composite functions. And that derivative of the composite functions means that there's a function within whatever else is going on. Now, the tricky part of this is understanding what is your inside and what is your outside of your function. It takes some practice, and they're easy to miss, so we're definitely going to work together on this. But the rule is this. When I have the derivative of a composite function, I'm going to take the derivative of the outside or the parent function, and then I'm just rewriting the inside function, not doing any math, not changing it, not taking the derivative, not simple, just rewriting that very, very, very same function. Then it's going to be multiplied by the derivative of the second function. Now this might remind you a little bit of the product rule. The product rule has a couple distinct differences. First of all, the product rule's got a plus sign in there, right? Not a multiplication sign. So make sure you pay attention to that multiplication sign. And our product rule is always like the derivative first times the second, the derivative of the second times the first, right? So this is not going to be the same as that conversation. So the derivative of the first times what's inside, and then the derivative of what's inside. And it's the chain rule because it continues to link on down. If I had 3 functions embedded, I'd have to do this process 3 times. If I had 4 functions embedded, I'd have to do this process 4 times. So, we're not doing that today. We're not doing that today. No. Not doing that yet. It's coming. All right. So the biggest part of this conversation would be recognizing what is the outside function and what is the inside function. So we take a look at this one, and it's f of x is equal to x squared minus 5, and that whole thing is to the 4th power. So our outside function is f of x is equal to something to the 4th power. Our inside function is that x squared minus 5. Take a minute and make sure that you can see that, because this that lives inside here is an embedded function into this conversation here about to the 4th power. You okay with that? Ready for the chain rule? When I take the derivative of this, I take the derivative of my outside function. So 4 times that function there's my derivative. That's fine. Now what I need to do is I need to go ahead and multiply it by the derivative of what's inside. So what's inside is this, and my derivative of that is going to be 2x. So the derivative of this composite function, and I can go ahead and simplify this to 8x times x squared minus 5 to the third power. Wait, where'd you get 8x? 4 times 2. Yeah. That's the derivative of the inside. So this 4 comes out front, power rule, right? My exponent comes out front. The derivative of that first, and then I just repeat this. I don't change it, I'm not doing anything. This was my inside function. So 4 comes out here, and this goes down a power. This is just what's living inside, not a problem. But now I need to take the derivative of that inside piece. So here's my 2, and then x to 1 less power. Because this is all being multiplied, I'm not going to bother making you multiply that out. We got better things to do. So that can stay fine, but these are easy multiplication, 4 times 2 and x. Now, sometimes the manipulation of how deeply we dive into the algebra becomes a conversation, especially if we're on something like a multiple choice test. If you're looking at a multiple choice test and you get this as an answer, but here sits this, then you know you need to go one step further. Sound okay? All right. For example 2, I would like your group to just talk about what is the outside and what is the inside function. On your mark, set, go.
Oh, I'm so dumb. That makes so much sense. I didn't know you.
Do we agree? Do we agree? Inside, outside functions? Okay. So notice with the square root function now, if you do enough of these, when I watch somebody do calculus, who's been doing this for a very, very, very long time, they don't bother to rewrite this to the 1/2 power because they have it memorized exactly what happens. Because they have it to the point of where they know that the derivative is always going to put a 2 in the denominator because the 1/2 comes out front, right? And they know that this power is always going to go negative when I subtract 1. So they know that they're always taking the square root. So think about that for a minute. And let's solve a simpler problem on the side. Ready? Let's talk about if y is equal to the square root of x, and we call that x to the 1/2 power, isn't y prime always 1/2 times x to the negative 1/2? And isn't that always 2 roots of x? So if you watch somebody do calculus who's been doing this for a very long time, they circumvent this whole thing, and they can go from here when it's time to take the derivative to here. So it's okay to start thinking about that, because when we see that all the time, I know that this power is going to come out front as a coefficient, and I know that it's always going to end up with 1 in the numerator and 2 in the denominator. And then I know that whatever's inside of here is now going to be to the 1 less than 1/2 power, or negative 1/2. The negative 1/2 power does 2 things. It moves it to the denominator and calls it a radical. All right, so that's my derivative, and I have to put that function inside. So that's going to be 4x minus 3. And then times the derivative of my inside function. What is the derivative of 4x minus 3? Yeah, 4. So now if I wanted to, I could say g prime of x is equal to 4 over 2 times the square root of 4x minus 3. And then I could go ahead and simplify this and say that g prime of x is equal to 2 over the square root of 4x minus 3. So that becomes that conversation of how far deep into the algebra do we go. If you're taking a multiple, I'm going to write that neater. If you're taking a multiple choice test, you go until you recognize an answer. Sound okay? Of course, we had to make it difficult by introducing your sine, your natural log, right? Is that one repeated twice? Oh, I know why it's repeated twice. Yeah, we're going to do it 2 different ways.
Oh God, it's crazy.
I know, 2 different ways. All right. Would you, for 3 and 4, please, with your group mates, identify which is the outside function and which is the inside function for each of these on your markers that go.
So is the outside the sine squared?
What, the outside? Let me assess that. Because it's, you get rid of with like direct words.
Yeah, I think it's negative cosine?
Is it cosine? Is it negative cosine? It's negative cosine. I'm pretty sure it's negative cosine.
The what? The sine?
Sine.
It's just cosine. It's just
So
cosine.
then the derivative of cosine is negative sine.
Yeah. But there's a square.
It's cosine squared. Yes.
So cosine of 5x times.
Yeah. I think it's fine.
Yeah, that's good.
So that's the one, is it?
This one Why is the element so
So you do, no, so it's, do the derivative of the outside, which is, which pushes the square root to the negative and puts it to the point, right? Yeah, and then you take, oh wait, I did this first.
That first function is the fact that I have something being squared. So that's, God bless you, that's my first function. So when I go to take the derivative, h prime of x, this is going to be equal this 2 times whatever is on the inside, now to the first power. So especially for sine and cosine, when we put that sine squared of x, remember the sine of 5x is a value. The sine of 5 times whatever function, whatever input value I'm talking about, whatever radian value. That is a set value. All right, so when I talk about 2 comes to the outside, this sine of 5x is my inside. So when I talk about finding the derivative of and then writing my second function, here's my inside value. And then I'm going to multiply it by the derivative of this, which is, so think about sine, cosine, and it's going to be 5 cosine of x. So this becomes, and remember the sine of 5x and the cosine of x, those are values. This is a coefficient, this is a coefficient. So my h prime of x is going to be 10 sine of 5x cosine of x. All right, so let's talk about this one. My outside function is my square root. And again, if you need to think of that to the 1/2 power, that's fine. But when I'm finding my derivative, I know that that 2 is going to be there, and that's going to result in something to the negative 1/2 power. So I can kind of just jump ahead to that. Times, what is the derivative of the natural log of x? So then I can go ahead and just say that y prime is equal to 1 over 2x square root natural log of x. Sound okay? All right, we'll go on to this one. Y prime is equal to, when I take the derivative of the natural log, we know that's 1 over x, right? And that x was my inside term. And then that derivative of that inside term is going to be 3x squared. Try to get better at drawing my boxes so you can see the derivative. So when I go ahead and I put that together, I get y prime is equal to 3x squared over x cubed, which then simplifies again to y prime is equal to 3 over x. We okay with that? So the cool thing about this is we have these exponent rules where I can rewrite this one, and keep in mind I'm not finding my derivative yet, but we have an exponent rule that allows us to rewrite something with an exponent by saying that's the same as 3 times the natural log of y. Well, I don't know why there's a y there. X. If I go to take the derivative of this one, 3 over the natural log of x is going to be 1 over x. So notice I got the same thing from both ways. So when we have something really simple, we can be reminded, oh wait, I can go back and do it that way. And that validates what we're doing with our inside-outside conversations. Sound okay? All right. So here's this chart. Given the table of values, find f of 4. Now remember, we're finding the slope of the tangent line at 4 for each function. And we have each of these different embedded functions. And if it helps you, you can see that your f of x is going to be your outside function of your g of x, which is your inside function. Your f of x is going to be the square root function. H of x is your inside. H of g of x. All right. So when we do this, we want to make sure that when we're finding h of 4 or f prime of 4, we need to set ourselves up with that chain rule. So f prime of 4 is going to be equal to the derivative of my original function. So when I take the derivative of this, the 2 comes out front, and then whatever g of x is equal to. So I know I'm plugging a 4 in, so g of 4 is 3. Are you okay with that? And then that has to be times the derivative of my inside function. So the derivative of my inside function at 4 is going to be a negative 2. So I wind up with 6 times negative 2. I wind up with negative 12. All right, with your group mates, see if you can work your way through the next 2 examples. On your mark, set, go. Okay, let's talk about it. Ready? So you don't need this other row until this problem. Any of you curious about why that row was there? Yeah, Steven's like, yeah, I was. All right, so let's talk about it. If my outside function is something squared, my derivative of that is going to be my 2 comes out, and then that function is going to be what is on the inside. So g of 4 has an output of 3. That's why that says 3 there. Got that? When I multiply it times the derivative of my inside, the derivative of my inside is going to be negative 2 at an input value of 4. And then the rest is just multiplying in order of operations. All right. My outside function is a square root. My inside function is h. So whether you need to simplify it and think of it as this to the 1 to negative 1/2 power, or you can just jump right ahead to knowing that 2 is in the denominator, and you're taking the square root of whatever that h function is. When I have an input of 4, the output of my h is 9. Times the derivative. So the derivative of my h function at 4 is 5. That's why that goes in there. And the rest is simplifying. So this is definitely a tricky one because we have this embedded function. We have that composite. So it's almost like the composite of a composite. So when I talk about having that function, I know I'm going to take the derivative of my first function times the derivative of what's inside. Now this first function, that input value of 4, g of 4, gives me a 3. So now I need to know what h of 3 is. 3 as an input to h as a derivative gives me negative 3. This is still an input value that I had originally of 4. So I still use 4 for this. 4 goes into g prime and negative 2 comes out. That's why that's negative 2. That's why that's 6. Yeah.
Why is there negative 3?
Why is there a negative 3? Truly, the only thing that we needed from this whole value is h prime of 3. And that's where that negative 3 comes from. So all of these conversations were unnecessary. This 3 is negative because I wanted to find, so just like we did over here, you did your input, and then that output became the next function's input. That's what happens here. I put my input of 4 into g. When 4 goes into g, do you see how 3 comes out? So because that was an embedded composite function, now I'm finding the derivative of an input of 3, which is why I need that second row. Here's my input of 3. So my derivative of my h with an input of 3, my output is negative 3, and that's why that's negative. Sound okay? All right. Real quick, I need to fix something. I screwed up on this one. This 5x is an embedded function within. So remember how I said the chain rule goes on and on and on and on? That 5 is the coefficient. It doesn't come out until you take the derivative afterwards. So let's go through this one again. My outside function, I take the 2 times my inside function, which is the sine of x. When I take the derivative of the sine of 5x, I have to follow the same chain rule. So the derivative of the sine of 5x is going to be the cosine of 5x, and then the derivative of that 5. So in the notes I originally gave you, I missed this 5. So you want to go back and fix that. So this 5 and this 2 is where I get my 10 from, and make sure that you add a 5 there. So this 5 and this 5 need to be added to your notes. Sound okay? All right, time to practice.